So in this video, we're going to discuss the derivative as the slope of the tangent line. And we'll explain what that means as we go along. So in the last video, we saw that our derivative of a function f at x naught, some point, is defined as a limit. So it's the limit of the average rate of change of the function over a small interval as that interval shrinks to nothing, to a point. So this is the formula. You take f at the right endpoint of your interval, subtract the value of f at the left endpoint, so that's the change in f. You divide by the change in x, and then you look at that quantity as delta x goes to 0. And what we want to do is interpret this formula geometrically in terms of the graph of f of x. We want to deepen our understanding of what this means by thinking about it in a different way. Okay? So here's the graph of a function. And we'll start with, so we have our x naught, that's in the picture here. We have delta x, the small amount of x, and we're going to take that and we're going to add it on to x naught. That'll give us our interval. So I can put, say, so my x naught plus delta x, right? That's going to be the right endpoint of the interval. And this whole interval here, the length of it is delta x. Right? And our function takes, so we have this value f at x naught, and then we have the value of the function at x naught plus delta x. Okay, so these 2 points here, those are sort of representing these values here, the value of the function at x naught and the value of the function at x naught plus delta x. So the first question is, what is this quantity here in terms of the graph? So remember, this quantity here, this is delta f over delta x, right? The change in f over the change in x. And f of x, we can give that a variable named y, right? So this is change in y, right? The change in the output y. And so measuring our outputs along the y-axis here. The change in y over the change in x. And while this should be familiar, right, this is a slope. Right, that delta y over delta x, it's a slope. And what it is it's the slope of the line that connects these 2 points here. And so I've indicated that in the graph there, it's that dashed line that's connecting, or line segment that's connecting those 2 points of the graph. And this is called a secant line. This is called a secant line of the graph of f, or of f of x. Okay, so it's the secant line of the function f of x, or the graph of the function f of x that connects x naught to x naught plus delta x. Or I guess more properly, the point x naught, f of x naught on the graph, which is here, and the point x naught plus delta x, comma, f of x naught plus delta x on the graph. Okay, so we can be more precise over here. This is the slope of the secant line. Slope of secant line of the graph. So that gives us an interpretation of this quantity here before the limit. So we're just looking at this quantity here without the limit for the second. So in other words, geometrically, this average rate of change of our function over this interval, we can think about that geometrically as the slope of this secant line. Okay, so it's the numeric, so the average rate of change of our function over this interval is the slope of this geometric figure, this line. Okay, that numerical quantity, the slope of that line is the same as the average rate of change. It's a way to visualize the average rate of change of our function, right? So the steeper this line that connects these 2 points, the more our function changed relative to our change in x over that interval. All right, so now we would like to invoke this limit. So we need a way to interpret this full expression geometrically with the limit included. And so for that, what we're going to imagine is that this delta x is going to 0, right? So as delta x goes to 0, this interval shrinks shorter and shorter and shorter, right? So you can kind of imagine a sequence of points that are shrinking back towards that point x0. Now I don't want the picture to be too crowded, so we're only going to look at a few points, but we're going to take a few of these points, look at their images up on the graph of the function. And that goes to there, that goes to there, that goes to there, and we'll look at the corresponding secant line and be thinking about the slope. So I've drawn in a few of the secant lines. So for this point here, this x point, and so delta x here, it's this small amount, and we look at the function at the right end point, and the slope of a secant line connecting those 2 points, and it's the secant line is this purple line here. The slope of that's the average rate of change over this small interval here. And then if we move a bit closer, so our delta x is now this short distance here, we look at our function, right, where it is, we form this difference quotient. This is called a difference quotient, and that gives us the slope of this secant line in red here. And so I just draw the line that connects these 2 points, and the slope of that line is the average rate of change of my function over that small interval. And then again, we can move a little bit closer, and we get this orange line connecting this point and this point on the graph. And so the slope of that line is the average rate of change of the function over this small interval here. So you see, as these points come closer to x0, the points on the graph come closer to the point x0, f of x0, and these secant lines, they're converging on a particular line in this picture. And the particular line is called the tangent line. So you can try to mentally imagine this point shrinking all the way back to this point here, and what line would result if you kept continuously forming the line connecting this point with this moving point here. What you would get is a line something like this. It's the line I've indicated in green here, and it's called the tangent line to the graph of the function at the point x0, f of x0. So I should probably indicate this blue point here is x0, f of x0. And this green thing is called the green line there is called the tangent line to the graph at that point. Okay, so the limit of these slopes of secant lines, right? So our derivative is the limit of average rate of change, right? Well, geometrically, we now interpret this as the limit of slopes of secant lines. Okay, so this quantity here geometrically represents the slope of the secant line. Once we take the limit, we get the slope of the tangent line. Okay, so the limit as delta x goes to 0 of change in f over change in x, which is just this thing over here, this is the limit of slopes of secant lines, and in that limit, right, once that delta x vanishes, we get the slope of the tangent line to the graph. And so this tangent line, it's a line that it goes through this single point on the graph and just touches the graph, right? So if we sort of were to zoom in here into this graph, the graph of the function and this tangent line would kind of just be making contact at this point x0, f of x0. So down here I've tried to give you a more zoomed in view of what the tangent line should look like. Roughly speaking, this tangent line, it goes off in the same direction in some sense as the graph of the function does. And so you sort of follow the graph of the function through this point, Right? The direction that this point is moving instantaneously as you move through the graph at this point is indicated by the direction that the tangent line is going. And so the tangent line sort of just kisses the graph at this point because it's indicating the same sort of direction that the graph is pointing. So to summarize, our geometric interpretation of the derivative, right? The derivative is this limit of the change in f over the change in x. The geometric interpretation of that is that it's the slope of the tangent line to the graph at the point x naught, f of x naught. Okay, so what that means is this tangent line, the equation of the tangent line, well, the tangent line has two properties. It goes through the point x naught, f of x naught. Okay, so the tangent line, it's going to have the equation, if we write it in point slope form, y minus f of x naught equals the slope of the tangent line, which we'll just denote m for the second, times x minus x naught, right? Because the tangent line goes through the point x naught, f of x naught, right? And what is this slope here? What is the slope m? Well, by definition, the slope of the tangent line is the derivative at x naught, right? So this slope m is actually none other than f prime at x naught. Okay, so this is the equation of this line, how you write down the equation of the tangent line to your graph. So to summarize, the derivative of f at x naught, or f prime at x naught, is the slope of the tangent line to the graph at x naught, f of x naught. And the tangent line, what is it? The way you can think about the tangent line is it's the line that most resembles the graph of the function f of x near x naught. And so it's the unique line that best approximates the function near this point x naught, f of x naught. And if we chose any other line other than this tangent line here, it would kind of go off at a weird angle to the graph. But among all the possible lines you can draw through this point, this is the unique line that sort of goes off at the same angle as your function f of x's graph. And so it most resembles the graph of f of x near this point x naught. Okay, so we fixed this point x naught, and for that particular point, this is the line that best resembles the graph of the function f. Or in other words, this linear function describing the tangent line here is the best linear function that we can use to approximate the function f near this point x naught. Okay, so that's the tangent line. It's the line that most resembles or best approximates the graph of f of x near x naught. And then the derivative at x naught is the slope of that line.